To question 3, as you can see, it starts by saying the nth term of a sequence is given by Tn, and they tell us that Tn is equal to 2n, Tn is equal to 2n plus 1 over the square root of n squared plus 1. That's Tn. And then the question that they ask us is to evaluate the limit of Tn. So part 1, evaluate the limit, and they want the limit as n is going to infinity of Tn. So the limit as n goes to infinity of Tn, what they're asking us to do is evaluate the limit as n goes to infinity of that statement over there, because Tn is equal to 2n plus 1 over the square root of n squared plus 1. When you're doing these limits, the first thing you need to do is divide through by the highest power of n. Divide through by the highest power of n. The highest power of n is n, so we're going to divide both the numerator and the denominator by n. Now look how I'm going to write n in the denominator. Instead of just writing n, I'm going to write n in the denominator as n squared square rooted. Isn't that still just n? Yeah, man. And so what we're going to get is the limit as n goes to infinity of Tn is equal to the limit as n goes to infinity of 2n divided by n is 1 plus 1 divided by n is just 1 over n over the square root of, now we can combine these using surds. Now n squared divided by the square root of n squared. N squared over n squared is 1 plus 1 divided by n squared is just 1 over n squared. Wait, how did I get to 2n divided by n is 2? That should be 2. My apologies, that should be 2. So when you plug in n as infinity now, what you're going to get is 2. 1 over infinity, 1 over a very big number is almost 0 or approximately 0. That becomes 2 over 0 plus the square root of 1 plus 0. And so the limit is 2. All right. So to conclude, let's write it right here. Therefore, the limit as n goes to infinity, the limit as n goes to infinity of Tn is equal to 2. That's that. The limit as n goes to infinity of Tn, that's equal to 2. Nice and easy. That's the limit as n goes to infinity, 2. That takes care of part 1. Let's look at part 2. Part 2 says, show that T4 is equal to that thing right there. So we need to show that T4 is that. Now T4, just let me separate the space. I don't want to squinch them up. I'm just separating them. All right, I did it lean. So down here is just going to be for working out T4. So T4 is equal to, substitute n as 4. So it's going to be 2 times 4 plus 1 over the square root of 4 squared. So over the square root of 4 squared plus 1. All right, so really and truly T4 is just, that's 9 over the square root of 17. That's T4. 9 over the square root of 17. All right. Now, this square root of 17 right here, we can rewrite this as 9 over square root of 70. Square root of 17, we can always break this up as the square root of, let me see, 17 is really, as we're saying right here, we're going to break up the square root of 17. And we're going to break this up as they want us to break it up. We need to have 9 over 4. All right, as you can see. All right, as you can see, it has 1 plus 1 over 16. So we're going to need to break this up. All right. I'm going to rewrite it as the square root of 17. All right, divided by 16, multiplied by 16. All right, you might wonder, where did that 16 come from? All right, where did this 16 come from? I am generating this right here. All right, generating that 4 right there. All right, and then I'm going to put a square root on it. All right, put a square root on it. And you might say, where that come from, sir? No, the root of 17 over the root of 16 times the root of 16. In reality, this root 16 cancels this root 16. So I didn't do anything incorrect. This is going to work out to be 9 over, now this part right here now, the square root of 16 is 4. So it's 9 over 4, all right, times, in this denominator now, I have the square root of 17 over 16. All right, nice and easy. So now all is left to do is simplify this part now. Now I can always factor out the 9 over 4. Right, it has 9 over 4 times 1 divided by the square root of 17 over 16. But the square root of 17 over 16 is just the square root of 17 over 16. I can rewrite 17 over 16 as, this is 1 plus 1 over 16. All right, nice and easy. And so what I'm getting then now is that T4 is going to be equal to 9 over 4 times, now, if I have it to the square root, 9 over 4 times that square root is to the half power. So it's 1 over, I can write it as 1 plus 1 over 16, 1 plus 1 over 16 to the half power. This is to the half power, all right? And then 1 over this, I can rewrite that then as 9 over 4 times 1 plus 1 over 16 to the minus half. All right, nice and easy, soft. That's how I finally rewrote it. Nice and easy and soft. No issues. Proven. All right, so we prove it. That's T4. Nice. So let's look at the next part of the question. The next part says, use a binomial expansion with x as 1 over 16 to approximate the value for T4. Now the binomial expansion that we're going to use is this formula. You have to remember this one, that 1 plus x to the n, I'm just writing it down, 1 plus x to the n is equal to 1 plus nx plus n times n minus 1 x squared over 2 plus n times n minus 1 times n minus 2 over 3 factorial, and 3 factorial is 6 x cubed, and that's the formula for 1 plus nx. So you're saying, sir, what are you saying? What I'm saying is replace x with 1 over 16, all right? And in this case, n is a minus half. And so that implies that 9 over 4 times, that implies that 9 over 4 times 1 plus 1 over 16 raised to the n is now minus a half. That's going to be equal to 1 plus nx. N is now minus a half, so 1 plus nx, which is minus a half. N is minus a half times, wait, left off something. It's going to be 9 over 4. 9 over 4 times all of this, which is 1 plus nx. Nx is, n is minus a half times x, and x is 1 over 16. Plus n times n minus 1. N again is minus a half. And so n minus 1 is going to be minus a half minus 1, which is minus 3 over 2. That's minus 3 over 2 times x squared. X, remember, it is x is 1 over 16. It's 1 over 16, x squared. All of this is being divided by 2. Plus, we need n times n minus 1 times n minus 2. That's going to be minus a half times minus 3 over 2 times minus 5 over 2. And that's divided by, of course, 6. Minus 3 over 2 times minus 5 over 2 times x cubed, and x cubed is 1 over 16 cubed. 1 over 16 cubed. And of course, it's all being divided by 6. Then you close that bracket. All right, so let's work this out now and see what we get. So remember, all of this is just T4. I'm going to replace that now with T4. So T4 is equal to 9 over 4 times. You put these in your calculator. That is 1 plus minus a half times 1 over 16. That's minus 1 over 32. Minus 1 over 32. This part going to work out to be minus a half times minus 3 over 2 divided by 2 multiplied by 1 over 16 squared. That is 3 over 2048 plus 3 over 2048. And you're going to have minus a half times minus 1.5 times minus 2.5 divided by 6 multiplied by 1 over 16 cube. That's minus 5 over 65,000 minus 5 over 65,536. Nice. That's what we get. So put all of that in your calculator now, and you tell me what you get for T4. You put what that you have, 1 minus 1 over 32 plus 3 over 2048 minus 5 over 65,536. And you multiply that by 9 over 4. And you get 2.182. You get T4 is 2.182. 2.18 to 3 significant figures. So that is T4. Nice and easy, soft. And it says to 2 decimal place. So this is it to 2 decimal place. All right, that's the answer to 2dp. All right, nice and easy, soft. Now let's look at part B. Part B says a series is given by, so you have a series. Part B, we have a series 2 plus 3 over 4 plus 2 plus 3 over 4 plus 4 over 9 plus 5 over 16, and it continues. All right. So this is that. All right. So I can call it maybe this right here. I can write it as 2 over 1. All right. Plus. What I want you to observe is that, let's say we're finding the nth term. The nth term would be, as you notice, it is just the first term plus 1. So it's r plus 1. So when r is 1, you get 2. When r is 2, you get 2 plus 1 is 3. And so it is just plus this. The nth term would be n plus 1 over, in the denominator, they're squaring it, over n squared. All right, so this is all we have. And so to write it in summation form, this is just the sum from, so if they say they want Sn would just be the sum from k equal 1. Sn is the sum from k equal 1 to n of k plus 1 over k squared. All right, that would be Sn. The sum from k equal 1 to n of k plus 1 over k squared. That's Sn. Nice and easy, soft. Second part. The second part says we're supposed to prove, hence, given that the sum from n equal 1 to infinity converges, show that Sn diverges as n goes to infinity. So we need to show that this diverges as n goes to infinity. Now, there are many ways you can do it. You can use the divergence test. You can use the integral test. There's so many things you can use. All right. You can use all of those. Now, let's say you wanted to use an integral test. All right. So using integral tests, let's say you wanted to use integral tests. You want to show that Sn diverges. Using integral tests, if it converges, it's going to go to a specific value. All right. And so using integral tests, you have the integral from k being 1, integral from 1 to infinity, the integral from 1 to infinity of, let's write, since they're using n down here, let's use n, the integral from 1 to infinity of n plus 1 over n squared dn. Now, if we're integrating this, you can separate it as the integral from 1 to infinity of, now n over n squared is just 1 over n plus the integral from 1 to infinity of 1 over n squared. Now they told us that this part converges, and they told us that that part converges to, I think they said it's pi squared over 6. All right, so that would be plus pi squared over 6 for this part. All right, that's what you're getting over that part. Now, right here, so now, what you're going to get is the integral of 1 over n is ln n, and ln n. When you integrate ln n from 1 to infinity, what's going to happen? The integral from 1 to n of ln n, when you plug in ln infinity, we don't know what that's a very big number. We can just call that infinity. All right, so this is infinity plus pi square over 6. Infinity plus pi square over 6, so hence it diverges. All right, so hence using integral test, it doesn't converge and so it diverges. So we can say hence using integral test, Sn does not converge, so hence Sn diverges. That's using the integral test. All right, nice and easy. Now let's say you didn't want to use integral test, you wanted to use divergence test. All right, you could use divergence test. What does the divergence test state? The divergence test tells us that if an, using the divergence test, so that's what we're going to do right here, divergence test. So the divergence test is if the limit of an is not going to 0, then it does not diverge. So using the divergence test, all we're going to have to do is find the limit as n goes to infinity of n plus 1 over n squared. Limit as n goes to infinity of n plus 1 over n squared. This is the divergence test. Now the limit of this is going to be equal to the limit as n goes to infinity of, we can again separate this as the limit as n goes to infinity of 1 over n plus the limit as n goes to infinity of limit of 1 over n plus the limit as n goes to infinity of 1 over n squared. Now we know that this part converges. This part is going to a finite limit. This part is going to a finite limit of, this finite limit is pi square over 6. But then what's the limit of 1 over n? The limit of 1 over n, this does not have a limit. As n goes to infinity, right? The limit of 1 over n, this part does not diverge. Now, how are you going to show that 1 over n does not diverge? Again, evaluating the limit of 1 over n, this part does not diverge. This part does not converge, I mean, all right? And so because this does not converge, all right, this part does not converge. And I know if you plug in infinity right here, you're going to get 1 over infinity is 0. But remember, it applies for the summation. It's really the summation. Remember the summation. So the summation of, you keep on adding, it's really the sum of 1 over n. If you're adding 1 over n, you're adding 1 plus a half plus 1 over 3 plus blah, blah, blah. And so it's never going to converge. As you can just say, this diverge. All right. And even if you want to say, look, all right. So as we can see, when you plug in infinity right here, you're going to get, this is 0, right? This is 0. And so the limit of this, n plus 1 over n squared, the limit of the final term is going to pi square over 6. But remember what divergent tests tell us. Divergent tests tell us that if an is not going to 0, then it diverges. All right, so since n plus 1 over n squared. So n plus 1 over n squared. It is not going to 0. N plus 1 over n squared. It is not going to 0 as n goes to infinity. It's not going to 0 as n goes to infinity. So it's not going to 0 as n goes to infinity, and hence it diverges. All right, hence diverges. That's another way to do it. So hence it diverges. So you can do it in any way you want. You can use integral test, divergence test, convergence test, you name it. D'Alembert's ratio test may not necessarily work here. You can use any one of those tests you want. Right? So we've shown that it diverges. Next part. Now the next part of the question says, use mathematical induction to prove that the sum, it says induction, so you're not going to use method of differences. It says induction. Use mathematical induction to show that the sum from r equal 1 to n of r into r minus 1. Use mathematical induction to show that this is equal to n into n squared minus 1 over 3. All right, that's what we're going to do. So of course, you start with step 1, you start with n equal 1. For n equal 1, what you're going to get on the left-hand side, you're going to get, this is equal to the sum from r equal 1 to 1 of r into r minus 1. And that's going to be equal to, when you plug in 1 here, you get 1. The sum from r equal 1 to 1 of plugging in 1. And you get 1 minus 1 is 0. 0 times 1 is 0. So you get in the first term as 0. All right, so the first term is 0. What do you get on the right-hand side? On the right-hand side, you're going to get 1 times 1 squared, which is 1 minus 1 over 3. And so you're getting 0. And so you can conclude that n equal 1 is true. So hence, n equal 1 is true. So the second part now is to assume n equal k is true. So step 2, for n equal k, you're going to have that the sum from r equal 1 to k of r into r minus 1, the sum from r equal 1 to k of r into r minus 1, that is equal to k into k squared minus 1, k into k squared minus 1 over 3. And you're going to assume n equal k is true. So you assume n equal k is true. Assume n equal k is true. Nice. So you assume n equal k is true. Now finally, we need to work out for n equal k plus 1. For n equal k plus 1, what you're going to get is n equal k plus 1. You're going to get the sum from r equal 1 to k plus 1. The sum from r equal 1 to k plus 1 of r into r minus 1. Don't freeze now. Into r minus 1. This is actually equal to, this is going to be equal to the sum from 1 to k. So it's equal to the sum from 1 to k of r into r minus 1 plus the k plus 1th term. And the k plus 1th term is going to be plus. The k plus 1th term is k plus 1 times k. K plus 1 times k. That's the k plus 1th term. Now the sum from 1 to k as we know it is k times k squared minus 1. K times k squared minus 1 over 3 plus this. Now we have k plus 1, or I can write it as k times k plus 1. Now this k times k plus 1, look what I'm going to do. I'm going to just put a 3 in the numerator here and divide it by 3. And you might say, sir, why would I do that? I'm going to do that so I can factor out 3 from it. All right, I need to be able to factor out 3. The next thing I want to do is factor out k plus 1. Now, k squared minus 1, as you recall, that's the difference of 2 squared. K squared minus 1 can be broken up as k plus 1 times k minus 1. Using the difference of 2 squared, that's just k plus 1 times k minus 1. So this is what we really have now in reality. In reality, we have k times k plus 1 times k minus 1 plus 3 times k plus 1. This is what we really have. And it's all being divided by 3. So all of this is being, all of this is going to be divided by 3. So then all we have to do now is factor out k plus 1 over 3. Factor out k plus 1 divided by 3. We'll factor out k plus 1 divided by 3. We're left back with, factor out k plus 1, we're left back with k times k minus 1. K times k minus 1 is just k squared minus k. And then factoring out k plus 1, we're left back with plus 3k. All right, nice and easy. We're left back with plus 3k. Now, you see this 3k? I am going to break up this 3k as this 3k. I'm going to break it up as I'm going to break up 3k as 2k plus k. That's why I'm going to break up 3k. I'm going to break it up as 2k plus k. And you might ask why. You might ask, sir, why? Why would you do that? Well, I noticed that k squared, and I left off the plus 3. My apologies, I left off plus 3 before I close that bracket. All right, it's freeze for a little bit. Computer freeze. Let's fix this now. Back to normal. All right, it's back to normal now. Good. Let's go. So k squared minus k plus 3k, right? Now, let's just simplify this in that bracket. Now that can be simplified to be k plus 1 over 3 in bracket. Now k squared minus k plus 3k can be left as k squared plus 2k. K squared plus 2k. Now k squared plus 2k, that's what I have in this bracket left. All right. But then k squared plus 2k, I can always rewrite that as, now this is where the magic comes in, all right? So now you have k plus 1 over 3 times, instead of k squared plus 2k, I'm going to write k squared plus 2k plus 1. You're going to say, what? Plus what? Wait, sir, plus what? Plus 1 minus 1. All right, and you might say, why did I do that? I did that because I know that k squared plus 2k plus 1 is k plus 1 all squared. So finally, my answer is going to be k plus 1, k plus 1, k plus 1 over 3 times this k squared plus 2k plus 1 becomes k plus 1 all squared. This becomes k plus 1 all squared minus 1. That's what I have now. All right, that's what I have now. K plus 1 all squared minus 1. Nice and easy, soft. Okay, so this is what we have now. K plus 1 over 3 into k plus 1 all squared minus 1. And so hence, we can conclude, therefore, n equal k plus 1 is true. Therefore, n equal k plus 1 is true if n equal k is true. Right? So what does that mean? And so by mathematical induction, by principles of mathematical induction, we can tell them that the statement given is true for all natural numbers. All right, that's your conclusion. That takes care of question 3. Nice and easy, soft. All right, now on to question number 4. And question number 4, it gives us a function. It says that g of x is equal to e to the 3x plus 1. So g of x is equal to e to the 3x plus 1. Let's hear what they have to say now. And they say that obtain a Mclaren series expansion for g of x up to x to the 4. So to obtain a Mclaren series expansion, first thing we're going to need is we need to differentiate this. So first thing, find what is g of 0. All right, so g of 0 is going to be equal to e to the 0 plus 1, which is e to the 1. So g of 0 is e to the 0 plus 1, which is just e. That's g of 0, just e. Then we need to find g prime of x. G prime of x is going to be equal to, when you differentiate 3x plus 1, you get 3. So that is 3 times e to the 3x plus 1. And so then that means that g prime of 0 is equal to 3e. It's equal to 3e. Then we need to find g double prime. G double prime of x is going to be equal to, we differentiate this now and we're going to get 9e to the 3x plus 1. And so what does that mean? That means that g double prime of 0 is equal to, plug in 0, we're going to get 9e. This doesn't look bad. And so now g triple prime of 0, g triple prime of x first, is going to be 27e to the 3x plus 1 So that means that G triple prime of 0 is equal to 27E. And finally, we needed to find G quadruple of 0. Well, find X first. And that's going to be 27 times 3. I think that's 81. So that's 81 e to the 3x plus 1. It's 81 e to the 3x plus 1. Right. So that is telling us that then G to the 4th of 0 is equal to, now 81 times e to the 3 times 0 is 0 plus 1. So let's get 81, 81e, 27e. So what does that mean now? That means that using Mclaren series expansion, we know that g of x is going to be equal to, it's equal to g of 0. It's g of 0 plus g prime of 0 times x, g prime of 0 times x, plus g double prime of 0 times x squared over 2, g double prime of 0 times x squared over 2, plus g triple prime, I'm going to write it as g3 of 0 times x cubed over 3 factorial, and 3 factorial is 6, plus g to the 4 plus g to the 4 over 4 factorial. 4 factorial is 24 times x cubed, x to the 4, sorry. Right. So it's g to the 4 of 0 times x to the 4 over 24. This looks messy. Let's fix this. G to the 4 of 0, x to the 4. Nice. So now let's plug in these now. So g of x is equal to g of 0. G of 0 is e plus g prime is 3e times x, which is 3xe, plus g double prime of 0 over 2, which is 9xe, 9xe over 2, 9x squared e over 2, because this is 9e, 9e over 2, yeah, plus g triple prime of 0, which is 27, so that's 27 x cubed, 27 x cubed e over 6, 27 x cubed e over 6, plus g to the 4, which is 81e to the 4 over 24, 81 x to the 4 e over 24. That is g of x. Now you may want to simplify it. I don't know, maybe you want to. Let's say you wanted to simplify it. Let's simplify it up here. All right, maybe you want to simplify it. I don't know, depends on you. And just if you want to, I'll simplify it with you. So simplifying it, we can write that g of x is equal to, as you notice, all of them have e, so we can factor out e. We're going to get e times 1 plus 3x plus 9x squared over 2, 9x squared over 2 plus 27 over 6 can be simplified. So 9 over 2, that's 9 over 2 x cubed 9 over 2 x cubed plus now 81 over 4. 81 over 24 can be simplified to be 27 over 8. 27 over 8 x to the 4 plus 27 x to the 4 over 8. That's if you want to simplify it that way. Doesn't matter to me. That's g of x. All right, I know it's kind of squint, so let me try to fix right here. Nine x cubed over 2 plus 27 x to the 4 over 8. That looks a little. All right, now that we finished that, now it says hence estimate g of 0.2 to 3 decimal places. So g of 0.2 is just going to be equal to, you're going to substitute x as 0.2 in the function here. So it's going to be e times 1 plus 3 times 0.2 plus 9 over 2 times 0.2 squared plus 9 over 2 times 0.2 cubed plus, you're going to put in finally now, that was what, 27 over 8? 27 over 8, 0.2 to the 4. 27 over 8, 0.2 to the 4. All right, nice and easy. So let's work out as a g of 0.2. So working that out, we have 1 plus 3 times 0.2 plus 9 over 2 times 0.2 squared plus 9 over 2 times 0.2 cubed plus 27 over 8 times 0.2 raised to the 4th power, and we multiply that by e. My final answer is 4.95. So I got 4.95. You want it to 3 decimal place, so it's 4.951. All right, just to check to see if we were right, this is our estimate. What you can do to check if you're right is work out what was g of x, e to the, so check to see if e to the 3 times 0.2 plus 1, check to see if that gives you the same thing. So you can just check that. If you get the same thing, you know you're correct. So 3 times 0.2 plus 1 is 1.6, e to the 1.6. Yes, they are correct. When you work that out, you get your 4.95. So no, so correct. All right, so this is just a check. All right, this is just checking to see if the absolute value is the same as our approximation. All right, so this is a check. This is just a check. Always good to check your answer. Nice. Now part B. Part B says, let f of x be equal to x minus 3 sine x. Part B. So they give us that f of x is equal to x minus 3 sine x minus 1. That is f of x. Cool. Now it says use intermediate value theorem to show that there has at least one root between minus 2 and 0. So first thing we can find is f of minus 2. F of minus 2 and f of minus 2 is equal to minus 2 minus 3 sine minus 2 minus 1. That will equal to minus 2 minus 3 sine minus 2 minus 1. That's equal to negative 0. Negative 0. That looks like negative 0.27. That is, of course, less than 0. So let's try to find out what is f of 0. F of 0 is equal to 0 minus the minus 3 sine 0 minus 1, but that is equal to negative 1, which is less than 0. So that gives us no indication if there's a root between minus 2 and 0. So let's try to bisect them and try maybe a number like 1. Try f of 1. So now f of 1, which is between 0 and 2, is 1 minus 3 sine 1 minus 1. So 1 minus 3 sine 1 minus 1. That's no good either. That's giving us a negative value. That's negative 2.52. So let's bisect 1 and try a number like a half. Maybe a half will work. All right, so let's try a half. When we try a half now, we get that f of a half is 0.5 minus 3 sine 0.5 minus 1. Let's try a quarter. Try a quarter. 0.25 minus 3 times the sine of 0.25 minus 1. 1.5. Oh, wait, I can't try 1. 1 is bigger than 0. My apologies. I needed to try minus 1. I was wondering why that wasn't working. Try minus 1. Yes, so this should be minus 1 minus 3 sine minus 1 minus 1. I was wondering how that was looking that way. So now we can try that minus 1 minus 3 sine minus 1 minus 1. That's 0.52. So this is correct. 0.52, and that is greater than 0. All right, and so since f of minus 2 is greater, since f of minus 2 is less than 0, and f of minus 1 is greater than 0, and minus 1, you can tell them, and minus 1, of course, is between minus 2 and 0, and f of x is a continuous function on the interval minus 2, 0, hence f of x has a root on the interval minus 2, 0. All right, that's the conclusion. Nice and easy, soft. All right, hence it has a root on the interval. Nice. Let's look at the next part of the question now. It says, use at least three iteration method to show that f of minus 0.538 is approximately 0 on the interval minus 0.7, 0.3. All right, so we're going to be using bisection method. So using the bisection method, I like to do it in the form of a table. It's easier for me when I put it in the form of a table using 3 iterations. So I'm going to use 3 iterations. I like to start with, this is AN, this is BN, then I find the midpoint M, then I find F of the midpoint. All right, nice and easy. We're using 3 iterations. All right, call this A, B, AN, BN, the midpoint M, this is F of the midpoint. All right, and just to write down back what was f of x, remember f of x is equal to x minus 3 sine x minus 1. And the values that they gave us to start with are, I think it's minus 0.7, minus 0.7, and minus 0.3. Now, if you find the midpoint of those two, minus 0.7 plus minus 0.3 divided by 0.2 is negative 0.5. Then what is f of 0? What is f of negative 0.5? You plug that up here and you're going to get negative 0.5 minus 3 sine negative 0.5 minus 1. And that is giving me negative 0.06. All right, nice and easy. Now, since it is negative, which is good, using 3 bisection, then that means that it falls on the interval. First, we need to check which one of these was negative. All right, so we needed to check which one is negative. So if you were to write down what was f of negative 0.7, just write down that. Just checking if that one was negative. Negative 0.7 minus 3 sine negative 0.7 minus 1. This one is positive. Right, so this one is positive, and this one is negative. This one is positive, and f of negative 0.3, f of negative 0.3 is negative. And so what that means is we can eliminate this 0.5 now. All right, so now we're actually in between 0.5 and 0.3. So we're going to write now that we're between 0.3 and negative 0.5. All right, now we're going to take the midpoint of those two, negative 0.3 plus negative 0.5 divided by 2. That's negative 0.4. Right. Find out what is f of negative 0.4. So you have negative 0.4 minus 3 sine negative 0.4 minus 1, which is negative 0.23. All right. Now f of, we know that this one, we know that the midpoint lies between this and this, and we know that f of this is negative. And so now what that means is that the root lies between negative 0.3 and negative 0.4. So let's continue. So the root lies now between negative 0.3 and negative 0.4. All right. Wait, let me see that. No, that's saying that the root lies between This is where the root lies. The root lies okay. Let's look at the second part. It says use at least 3 iterations of this interval bisection to show that f of minus 0.38 lies between minus 0.7 and 0.3. Okay, let's do that. So again, first let's write down what is f of x. So f of x is minus 0. F of x is x minus 3 sine x minus 1. And remember, we said that f of negative 0.7, put that in a calculator. F of negative 0.7, negative 0.7 minus 3 sine negative 0.7 minus 1. That's 0.23, which is greater than 0. And f of negative 0.3, that's going to be equal to negative 0.3 minus 3 sine negative 0.3 minus 1. That's equal to negative 0.41, which is less than 0. So now using the bisection method, bisecting that, we would get that the midpoint between those two is equal to negative 0.3 plus negative 0.7. All of that divided by 2 is equal to negative 0.5, I believe. Let me check that to make sure. Negative 0.7 plus negative 0.3 divided by 2 is negative 0.5. So now f of negative 0.5, that's going to be equal to, plug it in negative 0.5, plug in negative 0.5, that's negative 0.5 minus 3 sine negative 0.5 minus 1, that's equal to negative 0.06, which is less than 0. So from the first bisection, we're getting that the root lies now between, minus 0.5 and minus 0.7 from the first bisection. That's what we're getting. All right. So now let's bisect that part now again. So m is equal to now the midpoint of negative 0.5 plus negative 0.7. We divide that by 2. What we're getting is negative 0.5 plus negative 0.7 divided by 2. That's negative 0.6. Now let's find what is f of negative 0.6. F of negative 0.6, we plug that into the function, we get negative 0.6 minus 3 sine negative 0.6 minus 1, and that's giving us 0.09, which is greater than 0. And so which one was less than 0? As we can see, the root therefore lies between. So using the second bisection, the root lies on negative 0.5 and negative 0.6. So now we need to bisect that again now. So m is equal to bisect that minus 0.6 plus minus 0.5 divided by 2, you get negative 0.55. And so find what is f of negative 0.55 from the bisection. That's equal to negative 0.55 minus 3 times the sine of negative 0.55 minus 1, which is equal to 0.018, which is greater than 0. And so from the third bisection, the third bisection, the root lies on minus 0.5, comma, minus 0.55. All right. Good. All right. And so the midpoint of that now, the midpoint would be equal to minus 0.5 plus minus 0.55 divided by 2, which is minus 0.525. And so f of minus 0.525, that would be equal to all right, so you plug that in now. Minus 3 times that minus 1. I am getting 0.05. And so, did I do that right? No, I didn't do that right. Let me check that again. 0.525. That minus 3 times the sine of that minus 1 is minus 0.021, which is less than 0. And so the root lies on minus 0.525, comma, minus 0.55. And so if you take the bisection of that, the midpoint would be minus 0.525 plus minus 0.55 divided by 2. And now you get your minus 0.538. Right? And f of minus 0.538, that's going to be equal to, you plug that up there, you plug it up there, minus 0.538 minus 3 sine minus 0.538 minus 1. You put that in a calculator, minus 0.538 minus 3 times that minus 1, and you get 0.0076 or 0.076. That's what you're getting. Minus 0.538 minus 3 times that minus 3 times the sine of that minus 1. Oh no, minus 0.00741, and this is approximately 0. So we can write that this is now approximately 0. All right, and so that is shown using the bisection method. All right, so we can say hence minus 0.538 is an approximated root of f of x using the bisection method. So that's that. Nice and easy, soft. All right. Now let's look at the last part of this. It says use the Newton-Raphson method with estimate x1 being 5.5, approximate g of x, where g of x is sine 3x on the interval 5, 6. So the next part, it gives us a function g of x, and it says g of x is equal to sine 3x. So first thing, remember it said the first approximated root, it said the first approximation is 5.5. All right, so first thing we need to do is find what is g of 5.5. G of 5.5 is equal to the sine of 3 times 5.5, which is equal to g of sine of 3 times 5.5, that's minus 0.711785. So that's g of 5.5. Next thing we need is the derivative g prime of x. G prime of x is equal to, when you differentiate sign, you get cos. You get 3 cos 3x. So now we need g prime of 5.5. G prime of 5.5 is 3 times the cosine of 3 times 5.5. We put that in your calculator. 3 times the cos of 3 times 5.5. And I'm getting that's equal to minus 2.10719. So that's g of minus 5.5. Nice and easy, soft. All right. So now what does Newton-Raphson formula state? Newton-Raphson formula tells us that the second approximation x2 is going to be equal to x1 minus g of x1 over g prime of x1. All right, this is Newton approximation. But we already work it out, right? We already work it out. So it's going to be x1, which we found x1 they told us was 5.5, minus g of x1, which is minus negative 0.711785. And that is being divided by g prime of x1. And g prime of x1, we found that to be negative 2.10719. So you put all of that in a calculator, that will give you the second approximated root. All right, so I put that in my calculator. I'm going to get 5.5 minus, divide those part, minus 0.711785 divided by minus 2.10719. That's 0.337788. And so 5.5 minus that is 5. So I'll just write the final answer. The final answer, when I put all of it in my calculator, is 5.162. And how much decimal place it wanted it to? 2 decimal place, so it's 5.16. That's the second approximated root. Right? Nice and easy, soft. And that takes care of module 2. So let's go to module 3. All right, question number 5. Question number 5 says, Alicia's chance of getting to school depends on the weather. The weather can either be rainy or sunny. If it is rainy, the chance she goes to school is 0.7. In addition, she goes to school 99% of the sunny days, and it is